Indeed, I appreciate your folks arranging for a sunny day for me to be here. My wife could have actually vouched for this because apparently there's going to be a snowstorm tonight, so she'll be shoveling the driveway while I'm on the plane back, and the driveway will be all nice and clean when I arrive. So I seem to plan these distinguished lecture talks just around the snowstorms. Who knew when Albert suggested this date months ago that it would be snowing in Boston tonight? In any case, I'm going to be talking about airport security, and in particular the things that make our project, our approach, maybe unique, multistatic. I'll talk about what multistatic means. 3D is another aspect that's important. And we're looking for explosives. Of course we're looking for guns and knives, but you know, the gun sort of looks like a gun, and you know, machete looks like a machete, but a slab of explosives looks like a slab of something non-metallic without any particular form or shape. So we're trying to find ways of identifying these objects that are a little less well defined. And the challenge in this, of course, is humans come in all sorts of different shapes and sizes. The targets come in different sizes. What is normal? What is abnormal? Even just defining this is a challenge. Okay, so I'll talk about the current state of the art, what multistatic radar is and why we use it, the reflector system that we use to generate these beams that analyze the target, our elliptical toroidal reflector, a lot of fancy words there, but this is basically a fancy satellite dish for near-field focusing and imaging. Look at penetrable dielectric imaging, that is penetrable by waves. Waves don't penetrate metal, but they penetrate dielectric, like explosives, for example, and some of our experimental results. So most of you have been through one of these devices, I guess. This is the L3 ProVision system. You walk in, you put your hands over your heads. This is the jumping jacks that Alvin was talking about. You assume a position with your legs spread just enough to, well, I'll explain why. It does a very good job of distinguishing all sorts of stuff. In fact, let's see, I do. I usually travel with, well, you know, hard candy. I've got a little candy wrapper here. This will set off the detector. Now, why this could be considered a threat, I mean, clearly the threshold is turned way up so that there are very few misses. Everything is detected, even something as dangerous as a candy wrapper. So, but this is obviously an issue. If everything that you might forget to leave in your pocket, you know, sets off the detector, then is the detector doing anything except creating false alarms, alarming on everything? In fact, I did my own informal survey a few months back with one of these. A friend of mine and I were traveling. I went through TSA pre-check, went through very quickly through the other detector. He went through this thing. There were 10 passengers who I saw come through before my friend came through. Every one of those 10 passengers alarmed. But the false alarm rate was more than 100%. It was 110% because one person came through, was identified as having alarms, sent through a second time, alarmed again. So there were 11 false alarms for 10 cases. Well, if they took the machine away, there'd only be 10 false alarms for 10 cases. So is the machine doing anything at all? You know, I mean, it's really actually a very good piece of microwave imaging hardware, or millimeter wave, high frequency microwave. It does have some limitations, though. It has some dead spots, which if I had clearance, I wouldn't be able to talk about, but I do have clearance. I don't have clearance, so I can. There's no chemical information, so if you find something that looks like it has a dielectric constant of typical explosives, about dielectric constant about 3, relative dielectric constant about 3, well, so does nylon. So it doesn't distinguish a hazard like TNT from a block of nylon. Not that you'd have a 2-inch thick block of nylon on your back, but there is no chemical information specifically with millimeter wave imaging. The views are somewhat limited. After all, you have to be able to get into this device and out of the device, so there's going to be no detector in the entry point and the exit point, and so that limits the detectability a little bit. Poor penetration through leather and metallic clothing. Not a lot of metallic clothing out there, I guess, but if you're a motorcycle hood and you've got a pair of leather chaps, that might be a little bit confusing. Or if you're Lady Gaga and you go through with a dress made of meat, That would be problematic, I suppose. And certainly no penetration through skin or into body cavities. If you swallow, machete, it's not going to be detected. This is usually not, I mean, this is pretty tough to arrange this sort of stuff. This isn't, I guess if you're a suicide bomber, you'll do whatever it takes, but you know, to have a surgically implanted explosive is a pretty big, intensive and traumatic process. It hasn't really happened as far as we can tell, as far as DHS can tell, but this is a game of you know, of measure and countermeasure, with the adversary being increasingly more sophisticated. So the current system is based on technology that was actually written about and published in the IEEE Microwave Theory and Techniques transactions in 2001. I mean, that's 18-year-old technology. Certainly, the hardware has advanced, but the general imaging concepts are back where they were almost 2 decades ago. This is a nice image in that it sort of looks, it almost looks human. It doesn't look photographic, and actually, you know, frankly, the current systems have much better resolution and much higher bandwidth and do a better job of imaging. But they still have issues of, it looks like there's a tail maybe here, something going on between the arm and the chest. Well, there's nothing there. It looks like there may be, you know, light is shining through. Well, whenever there's a bright spot, it indicates the presence of something. This is actually the absence of stuff in here and here. These are dihedral artifacts that come from the fact that if you have a monostatic imaging system, that is, the rays come from a transmitter, bounce off the target, and go back to the receiver. If it's the same receiver as the transmitter, same antenna, monostatic system, then if there's a dihedral, that is 2 edges of a corner, the ray comes in, hits one side, hits the second side, and comes straight back, and it gives a strong positive response. That's why your arms have to be up over your head, and also why your legs have to be spread enough to minimize that dihedral artifact. Those bright spots shouldn't be there. Of course, every time I go through the ProVision system, instead of putting my arms like this, I test the system by putting my arms close to my head like that. So it produces a dihedral between my face and my arm, and I end up getting something like 18 yellow boxes right along my face, which is very confusing to the operators. They say, well, you know, what do you have in your face here? That's I'm not a good person to have in front of you when you're going through security at an airport. The other thing is that notice at the top of the shoulders are spectral dropouts. The rays that come from the detector bounce off the shoulder, head off somewhere else, and not back to the transceiver. They're not imaged, even though there certainly is a shoulder there. It's just absent from this view. Okay, so I've been throwing around the words multistatic and monostatic a little bit. Let me talk about the whole idea. With monostatic, what you have is up here we have a transmitter and a receiver co-located. It bounces off the target in here, comes back, and the same antenna is used for both. You might have multiple ones of these. So the second transceiver, third transceiver. This is multi-monostatic, multiple monostatic responses, and you can create an image from looking at a bunch of combinations of these. Then there's bistatic, where you might transmit from this point, scatter off points there, and receive at a separated receiver. And you could have multi-bistatic. But the best of all these would be a multistatic system, where you might have multiple transmitters and multiple transmitters and multiple receivers. In fact, I drew it with multiple transmitters here without showing the receiver lines, but the most effective means is when you have multiple receivers and you can digitally combine these for various points in the target region by adjusting the phases of each receiver signal. The analogy for this, for those who aren't electromagnetics folks, is suppose we all in this room had the job of, and the lights were out, and we all had the job of characterizing what the layout of the room was, where all the chairs are, where the podium is, where the, I don't know, the exit sign is, that door. And the room was dark, and we were all ushered out of the room, and each of us had a headlamp, And we had two situations. In one situation, each of us would come to the appropriate points where you're sitting with his headlamp on, looking everywhere, all around, see everything, recording anecdotally or even photographically where everything was, and then leaving. Next person comes in, does the same thing at his position. Next person, and after the 20 of you folks have all gone in, each looked around separately, you then try to reconstruct the room from the various positions. Well, since there's somebody over here and somebody over there, you could triangulate on lots of different points. That would work fairly well. But wouldn't it be better if everybody came in at once and all of you turned your headlights on or the headlamps on at once and looked everywhere at once? That's multistatic as opposed to multi-monostatic. So a little bit of just sort of geometry. Excuse me. We have an aperture, and we want to try to focus on a spot. This is near-field imaging as opposed to far-field radar. Far-field is when you want to look at, say, a Navy fighter in the air when you're on the ground, as opposed to near-field where you may want to have a sensor system that surrounds you, and you want to sort of try to see what's on person's body. The resolution is based on both the cross-range resolution, how narrow a spot is left to right, and the range resolution, that's distance from the aperture, the antenna that's sending signals out. The range here is calculated by the speed of light divided by twice the bandwidth of the signal. So if you have a wideband signal, you can get a narrow pulse. Makes sense. It's a Fourier transform relationship. Basically, the many frequencies produce a sharp impulse in time. That impulse in time, moving at the speed of light, produces a spot at a certain distance. But if you want to look at the cross-range resolution, that is, it's how narrow and how short the pulse is, that resolution is inversely related to this D, which is the width of the aperture. So a bigger aperture produces a narrower image, and the lambda in there is a wavelength. Shorter wavelength, that is higher frequency, produces a tighter band. And also, of course, the resolution gets, well, physically in meters, gets, the spot gets bigger, the resolution gets worse as you get further away. It makes sense if you're looking at things close in focused, as opposed to spreading out. Even if it's a tightly focused system, it still spreads out as you get further away. Laser pointer on the moon takes up a few meters worth of diameter. Okay, so ways of doing imaging. You might have a focus system like this. This is a dish that produces a spot, and if this guy is rotated back and forth and maybe spun around this way, shaken up and down, left and right, it could produce various scanning points across the target. So you sample at a particular point here, move the reflector, next point, next point, next point. This is an effective way of doing things if you have a good mechanical system. But this has got to shake fast enough so that between breaths of the subject, between heartbeats maybe, you scan across all, I don't know, maybe 200 by 500 points of the body. That's a lot of different points to go through in a second. So and you could do this electronically, but mechanically, you need a pretty good mechanical engineer to design a system that can do that. And to have that work day in, day out for 365 days a year for 10 years, a lot of maintenance on that. An alternative is electronically scanned phased array, where each antenna and receiver can be electronically steered, as it were. You could put mathematically adjust the phase and amplitude. This is a lot like phased array systems for early warning radar. And you can certainly scan across the aperture or the image space like that. Or a synthetic aperture where you have this guy here that moves back and forth mechanically, and by only having one or two radar heads, transmitters or receivers, you could, in effect, duplicate what this is doing, but you could do it sort of mechanically moving back and forth. That is, having a small guy move back and forth, sampling the field as if it were like this big guy, focusing the whole mirror back and forth. Those are the three main approaches. By the way, synthetic aperture radar is a export-controlled term if it's over 30 gigahertz, I guess. Maybe I should be careful about using it. In any case, so what do some type of images look like with one multistatic versus monostatic? This is multi-monostatic. We have a transmitter receiver up here. It sends down a signal, looks at it that way, sends it over this way, looks at it that way. And the creation, the reconstruction, the image is this yellow-orange spot right in the middle between the corner. Because anything that hits one side is going to bounce off and come back the other side. If it comes from this direction, it bounces off like that and comes back. So regardless of how you image this piece in here, you're going to get a strong response right in the center. If you do a multistatic system instead, you get, that is, you would maybe send a signal up like this and look at the response coming back this way. Notice the green ground truth is actually imaged pretty well with the yellow stuff. That's because the various angles of illumination make a big difference. This guy here clearly looks at what's bouncing off the edge, and this guy here looks what's like bouncing off that edge. So it creates a much better artifact-free response. Okay, this is sort of the general detection problem. Three general regions where you might want to investigate. If you could do this up in here, that is the distant observation, it'd be great if you could sort of see if somebody is a threat a football field away. Wouldn't that be wonderful? The problem is it's hard to get multiple views. It's hard to get from the left and the right and in front, maybe behind. If the sky is football field away, how are you going to surround this person? Your detector would have to be the size of a stadium. So although it does give some information from the limited view that you can see from right in front, it's certainly not multiple combined views. A little closer would be perhaps a truck. Maybe use this in a parade route, maybe drive to a scene where there might be some interesting activity. And then we're talking about, of the order of 5 to 10 meters away. This is still somewhat surreptitious. You might not know that you're being scanned as you walk by the side of a truck. And the people in the truck have still a margin of safety if this is a suicide bomber and intends to blow himself up. But this is, I guess, a compromise between the distant case and the sort of more intimately near targets that is less than 3 meters away. This is the portals that we've been looking at. You can get the most amount of information from this configuration, but the challenge is that, or the difficulty is that you're not a safe distance. So, in fact, you might, the security line itself might be a place where you would have to worry about, threats. Okay, so what can we expect from the imaging? This is an indication of models that we're using here to show what we have to contend with. If you're going to look at humans, you can't assume that humans are ellipses or circles or perfect planes. We can start with that perhaps, but in fact they tend to have interesting unsymmetric shapes. This is a view of a cross-section of an actual human frozen cadaver, which is available from an NIH site on the Visible Human Project. I guess this is liver. We've got some ribs in here. There's a spinal cord and a spinal cord there, and the spinal column around there. Arms with, I guess these are the humerus, the upper arm bones. I'm not sure what all this stuff in here is. Maybe we might have a little bit of stomach, perhaps. I don't know. In any case, fair amount of subcutaneous fat. This person's not obese, but certainly there is the white stuff is fatty. But there's skin on the outside, which is not visible, only about 1.5 millimeters of skin. And interestingly enough, if you're modeling this at 60 gigahertz millimeter waves, wavelength being of the order of 0.5 centimeter, well, a millimeter of skin, especially lossy skin, is enough to make the response from anything on the other side of the skin pretty much insignificant. So we could take this very complicated space and just really retain the outer boundary and code this up with skin indicated in blue and sort of body tissue in brown underneath. And this is enough to give a realistic model for forward scattering. So let's look at two cases. Just, suppose you have pipe bombs. This is the easy case because these are metal pipe bombs as opposed to explosives in plastic wrapping. But just to sort of see what this looks like, looking at the field difference between, well, the previous guy, which is without the 9 pipe bombs, and this guy with the 9 pipe bombs. All right, so what does this look like? Well, part of the reason this is challenging is because waves are complicated. This is a koi pond, actually in Hawaii. It's just a bunch of fish swimming around and a swan swimming by. But the point here is that you can see that the ripples, I mean, there's obviously stuff going on, but the ripples on the water are tough to analyze. That you can explain them. That is, they seem to be radiating out from disturbances, which makes sense. But figuring out what it was that caused those ripples is a real challenge. The other thing is that because I can present this in my talk for a distinguished lecture in IEEE, the trip to Hawaii was tax deductible. Anyway, so the response from the innocent case, these are like water waves. The blue stuff is like water waves on the surface of the water. If we compare that to the case, the dangerous case as opposed to the innocent case, you see the pattern is a little more complicated. And zooming in on that, the innocent case just looks like waves breaking at the shore, but the threat case, there's a lot of standing waves between the various metallic scatterers. So if we could grab these little dots in here, understand what those are relative to this, we certainly could pick out the effect of the scatterers, the metal pipe bomb threats. But we're not allowed to touch the person. This is close detection, but it's not within centimeters. So what happens to these little ripples as they get further away is what makes the problem somewhat challenging. All right, so our idea is to do this by sort of combining the synthetic aperture idea with a focused focusing reflector system. The idea is that if we have movement in one plane but not two planes, that is, we have a reflector that sort of scans up and down but creates a beam that is, instead of a spot, is actually a line, that there's it's less mechanically difficult, but it also takes advantage of the focusing that might occur physically through the reflector. We have multiple transmitters that illuminate this reflector, multiple receivers that capture the signal to make it fully multistatic and avoid the dihedral artifacts. So this will address those problems that were pointed out on one of the initial slides. Okay, so the idea is that we illuminate a slice of the body instead of just a spot. So instead of a spot like my green laser pointer back and forth, we illuminate the entire red reconstruction plane. We take the information from that, reconstruct a two-dimensional representation. So this is distance and this is cross range, and the dots in here indicate, for this case, the reconstructed intensity. We stack these for various positions of the antenna as it moves up and down, smooth them out, basically interpolate along that vertical direction. Look at things that seem to be sticking out, the stuff that's encoded in white, lighter colors are closer. We use that depth information rather than just intensity to give a sense of presence of objects. And the two objects that were simulated as being threats do pop out as reconstructed objects. Okay, so how do we do this? Now we take the simplistic geometry. Having just said it's important to use a realistic geometry, we now use a simplistic geometry, but this is sort of for instructional purposes. We have a torso that's approximated as an ellipse and two circular arms. We're just looking at trying to create a narrow slice in there, and that's created by using something that's elliptical in this direction, a reflector that's elliptical this way, and parabolic in the other direction. So it produces a beam that is actually focused vertically to just this narrow slice there, but it's got a bunch of straight rays that bounce off the target. We have a patent pending on this geometry. This can be extended to a toroidal geometry, torus being a donut. So we take we take this elliptical cross section in here, spin it around this axis of rotation, this revolution here, this red z-axis. So this is elliptical this way, circular that way. And if you put a focal point halfway between the circle center and the circle, then the circle ends up looking like a parabola. That's from second term calculus, I guess. And so it produces a bunch of collimated rays in the horizontal plane. The vertical plane focuses to this point right here because, as people remember, this is now, I guess, from 10th grade Algebra 2. If you have an ellipse and you put a laser pointer at one focal point, bounce it off an elliptical mirror, the rays will all focus at the second focal point. So that's the idea here. This is the first focal point. This is the second focal point. If it's an ellipse, every ray that leaves here will cross that guy. So here's an example, transmitter position. It illuminates the reflector, specifically right in front of it, high intensity right in the middle of it, and that produces a line focus right down there. If we take the second case, a transmitter might be here at 45 degrees. It illuminates this portion of the toroidal reflector, and that actually then creates a tilted focal region right there. So this guy, this focal point produces that plane, this focal point produces that plane, focal point over there would produce a similar one over in that direction. That's what it looks like. We milled this out of 4 separate hunks of aluminum. This is a block of aluminum, another second block, third block over to here, and the fourth block right here. These blocks started off being that thick, and 90% of the block, each block was turned into dust. It's a lot of heavy bags of aluminum dust that we had to dispose of. And in fact, if you look at the back side of it, let me just describe the surface. That's the toroidal reflector. That's the transmitter that's actually sitting on a fixed position. This is a receiver that's sitting on a rotating arc. This is the target that we image sitting on a the target is translated vertically instead of this complicated arrangement. This guy's moved instead. Presumably, you wouldn't want to put a human on an elevator and move him 2 meters in 2 seconds. That's a little rough. So it would be this guy being moved. But right now, for this experiment, moving this heavy piece of aluminum is a bit much. This guy looks like, it's actually relatively thin aluminum. It originally weighed 350 pounds. The whole thing now is about 80 pounds, so 2 people could lift it. Rough removal of material in the back. This is just sort of showing sort of the fast end mill that cuts away all this, the extra back of the reflector. The front of the reflector is the business end, as it were. So again, this guy is circular in this direction. The center of rotation is more or less where this pipe is. It's elliptical this way, so it focuses down to a slice, vertical slice in that direction. So some simulations at 0 degrees, 15 degrees, 30 degrees, and 45 degrees. These are different receiver positions illuminating different parts of the reflector. And you can see that in the focal region, it produces indeed a very narrow slice. We call this a blade beam reflector because it sort of produces a blade of intensity. So how does this actually work in practice? The reflector would be moved up and down along with its feed network. It works at 56 to 63 gigahertz. Resolution is about 25 millimeters in range. That corresponds to our 7 gigahertz bandwidth. So about 2.5 centimeters peak to peak in the range or forward imaging space. Let's see. Okay, so let me. There we go. So as this moves down, it illuminates the target region, which is the human, I guess. Let me run that again. It starts at the top, or it could start at the bottom. And the thing is, this has to move fast enough so that you can't, so that there's not, well, it's not really too crucial that the different slices are aligned. It gets a little blurry if one slice is moved relative to the other slice, but it's not as if the image hasn't been created yet before we gather all the information, as it is with the current synthetic aperture that's used by the ProVision system, the one in the airports now. With those, you have those masks that move across basically 120 degrees. They have to move fast enough so that you're not moving as you're being scanned. If you, while you're standing there, you sort of shudder or sneeze or hiccup, then the image gets all torn to bits. Which is another thing I've tried out, and it also gets the image all messed up. It's just a hiccup, that's all you need. This doesn't have that same problem because the image needs to be formed only in the cross section, and it sits there maybe 1/200th of the 2-second trip. So that's of the order of 10 milliseconds worth. So you don't really move very much in 10 milliseconds. All right, so some imaging results. We took a look at little metal box. This was the measured. This was the, let's see, I have this right. Which one's measured? I guess the one on the left is measured, the one on the right's simulated. The simulation looks pretty, the simulated results look pretty good compared to the model, the real measured results. Of course, a metal target is pretty easy. This one is a little bit more interesting. This is a curved torso simulant. Our system is moving pretty fast, but not at field rates because, well, basically we have to, accelerate the process. And frankly, this is something that we should get help from industrial companies who know how to do the engineering to make things, to accelerate and pipeline and make efficient timing issues. So we use a metal air duct as a simulant for the torso. This guy right here, well, let me show you what the ground truth is. This is a metal channel that's placed on the object. And to go back, if you look at that, well, I mean, maybe if you've seen these a lot, you might sort of say, yeah, that looks sort of like the range, cross-range image. However, if you filter it, and to do this, we use a radon transform, inverse transform. The radon transform is used for X-ray, CT imaging. The X-ray does, in effect, a radon transform. You then do a filtered back projection, which is the inverse radon transform, but filtering is very important to get rid of noise artifacts that lead to a fuzzy image. We did the same sort of idea here with inverse radon transform, but did no filtering because we wanted it to be fuzzy, because we want to fill in all the little slices. These are striations. These are artifacts of our system, I guess. We don't have the resolution to create that sort of variation. So we want it to be fuzzy, but we don't want it to be that fuzzy. That is, you want to take something that has this basic shape, but irons out all the dots, all the stripes in the middle, and that's what this guy over on the right side does. So this is the torso with the object on it. So pretty easy to do the inversion. Just to go back, can you, looking at this thing, see that there's a perturbation right there? Yeah, pretty much after my 30-second training course, you've all been able to pass and be able to recognize that. Okay. So the title does discuss that we're looking at trying to find explosives. We're trying to detect explosives that are non-metallic, that don't really have any particular form. So what do we use to determine that a foreign object? Finding a foreign object is not that hard, but finding the foreign object and characterizing it as a threat as opposed to a candy wrapper or a medical device or a money belt filled with cash or a lot of legitimate things that you might want to conceal under your clothing, but indeed are foreign objects. Well, so what is it? What can you take advantage of? Well, TNT has a dielectric constant of about 3, about 2.93, 3.1 or so, depending on its form. And not a lot of other things have that dielectric constant in particular. In fact, so few that it's tough to get surrogates. It turns out we use paraffin, beeswax, with a little bit of titanium dioxide. So if you look at the dielectric constant, a very narrow range, right around 3 with almost no conductivity, you know, you might be carrying an innocent block of beeswax under your clothing, but most people wouldn't. I mean, that's a pretty unusual thing to, you know, a medical device, yeah, okay. A Bible or a Quran or a bunch of cash, yeah, that might be reasonable. But a block of wax, well, you might expect to be searched for that. So we want to look at the dielectric constant as an indicator. So that there are multiple ways of viewing this, but the general idea is that if we send a signal down, it bounces off the skin, it comes back at an accepted or expected amount of time. If adjacent to a piece of skin, we have something that comes back, and it takes longer to go through a slab of dielectric because the velocity is related to the inverse square root of the dielectric constant. It takes longer to go in, takes longer to come back out again. By the time it comes back out, it's delayed. In effect, it makes the skin behind it look like it's depressed because it takes longer for that response to show up. So that's one approach, using a wideband system. The alternative is a focus system where you have a focused aperture. This is a different scanning configuration, single frequency, where we have an aperture that focuses to a point. If we're focusing to this point right here, can you see that in the audience? That's okay. You're focusing to that point right there, and in fact, well, you don't get the response if you focus at that point. You have to focus to the point that looks like somewhere above, about right there, because of refraction at the surface of the dielectric. In any case, in both cases, either with a focused single frequency system or the wideband system that we've been using in our lab, there's a response associated with the dielectric constant that is fairly tightly coupled to its value. Okay, that was that. And this is an example of what you might see on imaging if you could retain the distance aspect. So take a look to see if you can find the anomaly in here as this thing is rotated around. Rotating it around is useful from a visualization point of view, but if you look in particular right around it here, you guys see that depression in there? Play it one more time. This is a bottle, I think, filled with corn oil, which is not exactly the same as TNT, but it is penetrable, as waves can get through it. The waves take longer going through it, the velocity is lower. It takes longer for the waves to get through, so the reflection from the back surface just appears to come later, which means it looks like the back surface is deeper. This is a depression. Can you characterize this? Well, yeah, I guess about 4 years ago we published a paper on this. We look at two cases, one with a thick 4-centimeter object, one with a 2-centimeter object. In both cases, dielectric constant of TNT, and the response looks like this. This is a nominal skin on one side. This is a skin in the middle right here, and this is a skin on the right side right there. This guy produces a weak response from its top surface. Well, metal scatters a lot more than dielectric, so it should be weaker. But there's also a delayed response down here corresponding to the waves that make it through this, bounce off the surface, and then come back out again. Notice if it's thinner, then of course the response is well, not as far away from the nominal surface in both the secondary response and the front surface response. The formula for doing this in terms of these two distances, that distance and not the change in the front reflection surface, front surface reflection, and the delayed response from the skin behind it, these can be worked into the, I said there weren't too many equations in my talk. This is the one equation that's there. The estimated value of the dielectric constant is 1 plus that the delay associated with the back surface response divided by the front surface response, assuming you can measure those, squared. And notice if you put this in here, Well, this guy in here is about 4, this is about 3. You put it in, you get 49/16. It's supposed to be 3. Not too bad. Fairly simple formula. Certainly there are complicated, model-based, all sorts of difficult and challenging and exact formulae. The simplest are better when you're dealing with things that have random variation like human bodies and targets that are not exactly of known material characteristics. Okay, just some 3D imaging results from scanning the target up and down. This is a block of fake TNT. We can't really use explosives in our lab. Good thing. This is beeswax again with paraffin and titanium dioxide. It produces a nominal metallic response with a depression associated with the position of the dielectric. 2 guys. We have a depression in there characterized by the dielectric constant, penetrable dielectric object there. This thing's sticking forward, that's the metal channel, right, the metal channel and the dielectric, and trying to work at interesting graphics. I don't know if I mean, this produces a depression corresponding to that guy. This in here is a protrusion. You can see the protrusion here, depression on this side for that guy. Same, another view, but the same response. This one corresponds to the metallic object for imaging. Okay. So the last thing I want to talk about in the remaining 5-10 minutes is everybody's, well, at least the DHS and TSA's wish list, which is instead of going through a portal, spreading your legs, putting your arms above your head, and holding your breath, trying not to move or hiccup. What they prefer is just a hallway system, a walk-through system where you just walk between a pair of detectors. I guess a sign would be up saying you're being scanned, but the bottom line is that you wouldn't have to presumably, stay still or walk in a particular way. Actually, I guess it'd be better if you were on a moving sidewalk where you just kept your hands on the railing, whatever it is, on an escalator. I don't know what that's called, banister, whatever. But if you had your hands on those objects and didn't move your legs, then at least you wouldn't sort of change your position too much. But the challenge is that if you have a fixed array, say that big, however many inches or centimeters that is, this would be enough, presumably, to image this spot here with enough of an aperture to focus in. And if you want to go off to the side, well, to get the same angular capture, that is, you need this sort of angle to image this region. Get the same sort of angle there, you need an aperture that's this big. Well, instead of only being maybe 100, it's now 250 or so. It becomes untenably large. On top of that, we're only here at 45 degrees. How are you ever going to image something at the person's front? That is, if that's the detector and I'm walking by, it'll send rays out, but it'll bounce off my stomach and keep going. It won't come back to the transmitting system. It doesn't matter how big the array ends up being. So our thought is that you put transmitters on both sides, receivers on both sides, and have the transmitters talk to both sets of receivers. We'll have each side transmitter talk to both sets. And that way you can catch the specular rays that bounce off the person's front. So for example, if this is a person artistically rendered as, again, with a cylinder and cylindrical geometry where there's a torso and two arms, and the person is moving between down the hallway. Transmitters, I guess there are listed in here. I guess there's one behind the image there. So 9 transmitters on one side, 9 on the other, and 2 additional ones this way up and there. And a high density receiving aperture on both sides. As a person moves down this corridor, certainly we get stuff that comes back. But now what about this guy these rays all seem to be bouncing off the front of the person's stomach, but they can be picked up by receivers on the other side. That's the innovation. So, for example, we have a transmitter bouncing off a person's arm, picked up by a receiver in the aperture. That's fine. How about this guy? That's also picked up, has multiple positions. These aren't chronological. That is, the person is moving from left side to right side across here. Another case picks up that guy, pick up there. But now, if we want to image the person's front, we have a transmitter on the opposite side, and where's it going to reflect to? Receiver on the original side. And similarly, this guy here bounces off there, this one over here gets the back. And so you can see that you need multiple, that is, transmitters. Well, the bottom line is that not only do you need receivers on the same side as the transmitters, you need them on the other side as well. And having done all this, these all were picked up by a receiving aperture here. We do the same thing by a similar receiving aperture on the other side. And if you do this, you create, well, for receivers on one side, you create that one. And, oops. And you would repeat the same geometry for the receivers on the other side to get the other half of the target. Still some issues to be worked out, but the bottom line is that if you have receivers on the same side as transmitters and on the other side, which involves a lot of cabling across the path, either above or below the person, for precise alignment and multistatic timing and all, but it does provide at least the opportunity for being able to image a person without having him sort of pirouette in front of the sensor, which is possible but unlikely with grandma or kids or terrorists who want to defeat the system. Just not that likely to get compliance from passengers. Much easier if you just capture a person walking through a hallway. We actually got a patent was granted on this about a month and a half ago. It seems sort of silly that you could get a patent on, transmit here and receive here. How hard is that? But apparently it hasn't been suggested, so we did get the patent on it. Now we have to tell people that when they come up with this, that they have to give us $1 for every system they build. Okay, that's going to be the conclusion. I talked about this blade beam reflector idea of focusing to a narrow slice in the horizontal piece. The idea of that, one further analogy, I guess, is like there was a fellow who was searching very carefully one night under a street lamp, and his friend comes up and says, "Will you lose something?" He said, "Yeah, I lost my wallet earlier today." And friend says, "Well, you lost it around this light here somewhere?" And the guy said, "No, I was across the street." He said, "Well, why are you looking here?" He said, "Well, the light's better over here." Right? So the idea is that if you eliminate just a narrow slice, well, you're not looking at anything else. You're by darkening, in effect, everything else, you're not letting that clutter your image. So you're just examining that slice. Now, if you move to the next slice a little higher, you can get an image of the next slice up, and you add all those slices, you can get the full 3D image. You do have to have that motion, but at least you have motion in one direction and not left, right, as well as up and down, which really requires a lot of mechanical complexity. We've built and tested this at 60 gigahertz. We've been using custom chips by ADI, inexpensive chips of the order of $100 a channel. These are not designed as radars, but we've configured them as such by using the sort of separated radio receiver and transmitter with separate, so 60 gigahertz system with separate local oscillator synchronization clocks. The idea is that if you run a reference line as well as a line through the air, the amplitude and delay associated with the line through the air, in effect, becomes a radar signal. And as long as you process that intelligently, you get a nice radar using hardware that costs what a radio costs, $100 a channel, as opposed to, I guess when we first started this, about $250,000 for a radar channel. Of course, Raytheon makes pretty good radar, but for the imaging application where you want lots and lots of channels, you know, we have 50 receivers and 7 transmitters. I mean, all right, so that's I don't know, 30, yeah, so maybe $30 million or so, something like that. This whole thing is much less expensive at $100 a channel. Okay, so we talked about 3D reconstruction, minimal artifacts. Yeah, because it's multistatic, there's in effect no dihedral effects, which avoids a lot of the headaches of the current system, and we appreciate that. I do want to thank the Department of Homeland Security who funded this effort. We're actually on the 12th year of a 10-year grant. They like our work and sort of continue supporting our work, and we appreciate it very much. With that, I'll conclude my talk. Thank you.